Last time we proved the sum law for limits, which is 1 in this list, and I advertised that we would prove 5, which is an abstraction of the arithmetic laws, next in order to deduce all of the arithmetic laws from property 5. This is sort of an abstract arithmetic operation here, this box. But we will actually deduce 5 from 6, and so the next step in this work is to prove this composition law for limits. So we're going to prove property 6. We're assuming that we have two functions, f and g. We have a metric space x, and g operates on that and takes it to a metric space y, and then f operates on that and takes us to a metric space z. We're assuming that the limit of g of x as x approaches x naught is y naught, and then we're trying to calculate the limit of f of g of x, and the statement here indicates that we can pull f outside of this limit. So that's what we're going to prove next. Now, we're assuming that the limit of g of x is as x approaches x naught is this value y naught, and we're assuming that x is continuous at y naught. I want to write out both of the limit definitions of these things. To say that this limit is equal to y naught is to say that for every positive epsilon, there exists a positive delta, such that for every x in the metric space x, if 0 is less than the distance between x and x naught is less than delta, then the distance between g of x and the limiting value y naught is less than epsilon. So that's what it means to say the limit of g of x as x approaches x naught is y naught. We're also assuming that f is continuous at y naught. So what does it mean to say f is continuous at y naught? Of course, we're going to use the epsilon delta definition of continuity of f. So that means that for every epsilon in greater than 0, there exists some delta greater than 0, such that for every, now I can say for every x, and it's tempting, but the domain of f is y. And so I think it's more natural to say for every y in the metric space y, then if the distance between y and y naught is less than delta, then the distance between f of y and f of y naught is less than epsilon. So that's the epsilon delta definition of the continuity of f at the point y naught. However close we want f of y to be to y naught, that measured by epsilon, we can get it that close by making y sufficiently close to y naught using a sufficiently close proximity value of delta here, and delta is positive. Okay, so now the goal is to prove this, and that, of course, is also an epsilon delta statement. We're trying to prove for every positive epsilon, there exists a delta such that for every x in the metric space x, if the distance between x and x naught is less than delta and greater than 0, then now this is a little bit tricky here. The function involved is f of g of x, and the limiting value is f of y. So the distance between f of g of x and f of y is less than epsilon. That's what we want to prove. And this is almost as simple as just assembling these two previous values. We have this continuity of f. Now, this is phrased in terms of epsilon delta. And so what we're going to do is we're going to choose a delta for the epsilon here, but it won't be the delta that's required in this thing. And so basically, we have a nomenclature problem here. We're going to apply the epsilon delta definition to pick a delta for this, but we're not going to call it delta because it won't be the final thing that we need to do. So let's write the proof, and hopefully there's enough room to write the proof right here. So, so this is our goal statement. I need to pick an arbitrary epsilon, and I need to illustrate how we can find this delta. So let's choose an epsilon. Now, I need to choose this delta. I don't know how to choose it yet. But I do know how to invoke the definition of continuity of f. I can invoke that, and I can produce a positive number which makes this true. And I'm going to produce such a positive number, but I'm not going to call it delta because it isn't the thing that solves this problem. So I'm going to call it rho for epsilon in the definition of f is continuous at y naught. So basically, the rho that I'm choosing is the guaranteed delta here, which is guaranteed to exist by the assumption that for every epsilon there exists a delta. So I'm going to choose the rho for this. Now, rho is a positive number. I don't know what number it is, but it's a positive number. And I've assumed this about the limit of g. And that says for every epsilon, there exists a delta. Rho is a positive number. This epsilon stands in for any arbitrary positive number. And so I can apply this definition of this limit, I can apply this knowledge to the value rho instead of the value epsilon. And so how does that look? That looks like we just need to say, choose rho for, no, sorry, we already chose rho. We're going to choose delta for rho in the definition of this limit. So the limit as x goes to x naught of g of x is equal to y naught. All right, now having made these choices, I think it's useful to spell out what we know about these values. So I'm going to erase this theorem statement and spell out what we know about what's happening with rho and delta. So our assumption about rho guarantees to us that the choice of rho guarantees to us that this statement, is that the right? Yes. So this statement is true if I put a rho in here. So what we know about rho is for every y in the metric space y, if the distance between y and y naught is less than rho and greater than 0, then the distance between f of y and f of y naught is less than epsilon. So that's what I know. That basically comes from the choice of rho. So also, we know that because of the way that we chose delta for rho in the definition of this limit up here, we know that for all x in the metric space x, if the distance between x and x naught is less than delta and greater than 0, then the distance between g of x and y naught is going to be less than rho, because we chose delta for rho in this definition. And you can see what we're setting up here is to chain these two things together. So now let's assume that we have an x in x, which is actually the correct next step in our proof, right? So notice that we've let me highlight this in a different color. So in terms of the appropriate structure of this limit proof, for every epsilon, let epsilon be arbitrary, there should be a delta. I have chosen delta, right? Sort of skipping over the other stuff in between. And now the next thing I need to do is I need to argue about for every x. And so that's what I'm going to do. I'm going to say, let x be in x, okay? And then, of course, what are we going to do with the x? We're immediately going to assume the left-hand side of this implication. And so this is consistent with our proof structure that we're looking for. And then we're going to assume that 0 is less than the distance from x to x naught is less than delta. So that is totally consistent with the proof structure demanded by this limit definition. And then all I have to do is prove this. But in order to get this, all I really have to do is chain together these two implications that have been assumed up here. So, so notice that I have, by the choice of delta depending on rho, I have this statement, this implication, and I also have now assumed the left-hand side of it, and so I should conclude this. So then the distance between g of x and y naught is less than rho by, and let's call this double star, where this one will just be star. So this indicates that the distance between g of x and y is necessarily less than rho. Now, here's where things get a little bit sneaky. So this implication here is true for all y in the metric space, and g maps into the metric space y. So this is true for any little y in the set cap y, and g of x is such a y. And that means that this is necessarily less than rho. And that means that we can chain together this implication here. So what we know then is that the distance between f of y and f of y naught then must be less than epsilon by star. And the basic reason here is that g of x is in the metric space y. And sorry, I shouldn't have said f of y. I should have said f of g of y, g of x, because it's g of x to which I'm applying this knowledge. So that's chaining together this thing where the y that we're taking is the value g of x. And that means as desired, right? Because that's the appropriate conclusion here. That's what we wanted. And so this establishes the limit definition of the composition of the functions f of g of x under these two assumptions.